Good morning. So today we'll go over the last part of chapter 5, namely the simplex algorithm, this time to solve the minimum problem in standard form. We will focus in the beginning on how to actually bring the minimum problem into a maximum problem, because the whole idea is to actually create what's called a dual problem, which will be basically a maximum problem in standard form. So starting with a minimum problem in the standard form, we can create a dual problem, which is a maximization problem that will give us indirectly basically the solution, directly the solution of the minimum problem. So it's kind of like a trick, if you want. You change or you transpose some conditions and the objective function to begin with, and you work a problem that becomes a maximum problem, but which in fact will give you the solution of the minimum problem. So this basically makes it easier in the sense that the algorithm, when you go over the pivoting steps, it's exactly the same like for the maximum problem. The only difference is that we need to create that dual maximum problem. This is better understood over an example before we actually list the steps. And you should have also the simplex help sheet in front of you, because all these steps are described over in that handout. We will write it down here as well. But as usual, I'm gonna choose an example to begin with that can be solved via the graphical method, just to illustrate that indeed this method actually gives you the solution. Because in the graphical case, you can actually visualize the feasible region. And in the interest of time, I'm gonna just sketch the feasible region. You should take maybe 5 or 10 minutes, pause the video, and as an exercise, just solve the problem graphically yourself to convince yourself that that's the solution. So let's actually establish what we mean by a minimum problem in standard form. So the minimum problem in standard form needs to satisfy the following requirements. The variables are non-negative, just like before. That means xi greater than or equal to 0 for x1, x2, x3, however many variables you have. The other condition is that the constraints are greater than or equal to any constant. Okay, so notice the difference. In the max problem in standard form, you need to have less than a positive. This time around, it needs to be greater than any constant. It doesn't matter if it's negative or positive. And a third condition is that the coefficients of the objective function, which this time around we're going to denote it by C, are positive. So the coefficients of the objective function need to be positive this time around. We call it C because that suggests the idea of minimizing the cost, right? P for profit, it's a reasonable quantity to imagine that you need to maximize. That's for the maximum problem. C coming from the cost is a reasonable amount, kind of quantity to minimize, though again in various problems, what you minimize doesn't have to be a cost. For example, you can minimize the number of calories in some combination of meals. So let's start with an example right away. And suppose that the constraints are given by x plus y greater than or equal to 2, x plus y less than or equal to 3, 4x plus y greater than or equal to 5, and suppose that we need to minimize the objective function c equals 3x plus y. Okay, so if you solve this via the graphical method, and again, really take my advice to pause and do this on your own. I know that many of you don't do that. I just mentioned here so that you don't think I'm living on a different planet. I know that some of you don't even watch these videos, but even if you watch them, they may skim through it too quickly. That is not good, and it's not going to accomplish much. So pause the video, do the feasible region, find the corners, take those 10 minutes and do that. Plug the corners into the objective function over here and figure out what the minimum is. Okay, so assuming you did that, you should end up with the following picture. X plus y equals 2 is this line. And let's see, there's another one parallel to this. See, I'm gonna squeeze it here. This is gonna go through the points 3, 0, 0, 3. And the one kind of all the way across, like that. That's the line corresponding to the last condition, 4x plus y equals 5. If you compute the intersection points, these corners correctly, because the feasible region is going to be the interior of this quadrilateral. So you're going to have another corner here of coordinates 2 over 3, 7 over 3, and the corner here of coordinates 1 and 1. So when you plug in the corners via the graphical method into the objective function, you're going to have to test basically 2, 0, 3, 0, 2 over 3, 7 over 3, 1 and 1. And you can speed up the process a little bit. For example, clearly this one is not going to give you the minimum because, you know, if you plug in 3 and 0 for x and y, clearly you can plug in something less than that, right? I mean, if you plug in 2 and 0, that gives you a lower value, right, than the previous one. The question is in between these guys. If I plug in 2 over 3, so that's 3 times 2 over 3 plus 7 over 3. That's 7 over 3 plus 2. 6 plus 7, that's 13 over 3. That's like 4 point something. 4 point some decimals here. Let's see if we need to actually find that exact value. So if I plug, I don't have to find that because 1, 1 is obviously the minimum, right? So if I plug in 1, 1, 3 times 1 plus 1, that's 4. So clearly this is the minimum. Because 2 over 3, 7 over 3 gives you a quantity greater than 4. So the minimum is attained. Keep this in mind because this is what I want to focus on as we move on to the simplex method. So keep this in mind that the minimum is attained for x equals 1, y equals 1, and the minimum cost function for that value is going to be 4. So the minimum value of c is 4 attained for x equals 1, y equals 1. Okay, so how do we, this is basically just to illustrate what the simplex algorithm does, right? Because when you use the simplex method, you're not going to do the graphical method. This is just to compare the with what you get in the end. So the first thing to do is to make sure that your minimization problem is in the standard form. And if it's not written in the standard form, you need to bring it in that form if possible. So one of the conditions, I forgot to mention here that x is positive, y is positive. Always assume that this is given already, right? Because I mean, otherwise these problems are not going to be in the standard form. So the fact that these are non-negative, that's satisfied. Let's focus on the constraints, right? It says that they should be greater than or equal to any constant. So you need to change any inequality in the direction greater than or equal to. So that means the second inequality, the second constraint, you need to multiply it by -1 to revert the direction of the inequality. So we're going to end up with x plus y greater than 2, minus x minus y greater than -3. Remember, we have to change the signs. And then the last condition, 4x plus y greater than 5. And we need to minimize c equals 3x plus y. So this is now in standard form. right? All constraints are greater than any constant. The minimization, the objective function, is with positive coefficients. Here's how we're going to create the dual. Pay attention to this part here. We're going to write the coefficients in a matrix form. In this order, that's very important. Constraints first, objective function. So write all the coefficients, 1, 1, and 2, including the right-hand side, -1, -1, -3, 4, 1, 5, 3, 1, and 0. So think of a right-hand side 0 for the objective function. So this isn't a simplex tableau. Just to keep in mind here, this is not a simplex tableau yet. This is simply collecting the problem, the minimization problem in standard form in this matrix format in which the right-hand side of all of these coefficients are in this order. So I put this vertical bar just to isolate the right-hand side. Once again, coefficients of the constraints first, and on the last row, the coefficients that appear in the C row with 0 on the right-hand side. Then we're going to create what we call the dual problem by transposing this matrix. Transposing this matrix means interchanging the rows and columns. So we have the rows 1, 1, 2, -1, -1, -3, and then the other two. We're going to interchange the rows and the columns, and now the matrix that we have over here becomes 1, -1, 4, and 3, followed by 1, -1, 1, and 1. Okay, so column 1 becomes row 1, column 2 becomes row 2, and then finally the right hand side becomes the last column, row 2, -3, 5, and 0, and again copy that vertical bar. So you're going to interpret this as the coefficients of a new so-called dual problem. In variables, so since this is still going to be interpreted as the right-hand side, in variables y1, y2, y3. So you're going to have 3 columns. So basically you think of this new problem as a problem in y1, y2, y3, a maximization problem with the last row denoting the P equation or the objective function. So once you transpose this matrix, what you end up with here, basically, like I said before, should be interpreted as the coefficients of a new maximum problem. So we're going to have what is called the dual maximum problem, which will be in standard form if the minimum problem is in the standard form to begin with. So how do we read these coefficients? Well, each row represents a condition on the maximum problem in the standard form. So that means we're going to have y1 minus y2 plus 4y3 less than or equal to 3, followed by y1 minus y2 plus y3 less than or equal to 1. And we need to maximize P equals 2y1 minus 3y2 plus 5y3. Okay. So let's pause for a moment before we solve the dual problem and show you how you read the solution of the minimum problem. Let's again review what we just did. So starting again from scratch with a minimization problem in the standard form. Once you make sure it's written in the standard form, write in some sort of a matrix like this the coefficients of the constraints and of the objective function. But again, make absolutely sure it is in the standard form for a minimum problem, right? Greater than or equal any constant, coefficients of the zero of the objective function positive. So the interpretation of this matrix is that the first, with the exception of the last column, each column represents one variable, right? Since we started with two variables, x and y, then we have the variables, the columns corresponding to those variables. Then we're going to transpose this matrix. And notice that the last row becomes the last column. And because you're going to interpret this transpose as the coefficients of the maximum problem, you see why actually we needed positivity on the zero, because the zero becomes the right-hand side. And for a maximum problem, remember the right-hand side should be positive. I mean, because in the maximum problem in standard form, you need each condition to be less than or equal to a positive number. So once you transpose this matrix, you're going to interpret this matrix as giving you the information, the coefficients, for a maximum problem in standard form. So each row represents an inequality in the direction less than a positive. And you have new variables of the dual problem, right? So y1, y2, y3. And then write down the condition for that row, y1 minus y2 plus 4y3 less than 3. Y1 minus y2 plus y3 less than 1. And the last row, like I said, is going to be the P row. From this point on, you're just going to solve the dual problem. So you're going to introduce the slack variables. So you're going to write y1 minus y2 plus 4y3 plus s1 equals 3. y1 minus y2 plus y3 plus s2 equals 1. And remember, you're going to move the coefficients in the P row to the left-hand side. So this is basically what you did in 5.2. The only difference will be at the end when you read the solution. Because remember, what you solve right now is not the original problem, but the dual maximum problem corresponding to that first minimization problem. I want to make sure double check something. So 2 minus 3, 5. I gotta double check something. So 4x plus y. Okay, so let's move on with this. 310. I want to double check something before I move on. 2 minus 3, 5. Minus 2 plus 3 minus, okay, all good. So let's set up the simplex tableau. So first of all, the coefficient of P. So we're going to have P, Y1, Y2, Y3, S1, S2, and the right-hand side. I was going to look to see if it's just one pivoting operation. I'm not sure if, because I don't want to make it too long. So 0, 0, 1, 1, 1, minus 2. Y2 is minus 1, minus 1 and 3. 1 minus 2, minus 1, minus 1 and 3. 4, 1, 3. Not 4, 1, 3. 4, 1. Minus 5. So 0, 0, 1, 1, 1, minus 2, minus 1, minus 1, and 3. That's correct. and then 4, 1 minus 5, and then the slack variables, and the right hand side 3, 1, 0. Okay. So the first pivot should be in the first column, because it's in the second column, because that's the first negative entry, and the minimum ratio 1/1, 3/1 gives you this pivot 1. So we're gonna do row 1 minus row 2, and then 2 plus row 3. 0 minus 0, 1 minus 1, minus 1 minus negative 1 is another 0, 4 minus 1 is 3, 1 minus 0, 0 minus 1, and 3 minus 1 is 2. And then 1, 0, minus 1 times 2 plus 3 is 1. 2 times 1 minus 5, that makes it minus 3. 2 times 0 plus 0 is 0. 2 times 1 plus 0 is 2. 2 times 1 plus 0 is 2. Okay. So we still need to pivot because we still have a negative entry in the last row. Over here, the minimum ratio is, let's see, 1/1, 2/3. So that's going to be the pivot. Let's see, we divide by 3 first to make it 1. And then 0, 1, minus 1, 1, 0, 1, and 1. 1, 0, 1, minus 3, 0, 2, and 2. And now let's do row 2 minus row 1. And then 3 row 1 plus row 3 to make zeros below that pivot. So let's copy the first row. Zero minus 0, 1 minus 0, minus 1 minus 0, 1 minus 1, minus 1/3, 1 minus negative 1/3, that makes it 1 plus 1/3, that's 4/3. And then 1 minus 2/3 makes it 1/3. Okay. And finally the last row. Let's see. Let's see, still 1. 1 times 3 minus 3 is 0. 1 times 3 times, over 3 times 3 plus 0 is 1. And finally 3 times minus 1/3, which is minus 1, plus 2 is 1. And then finally the last piece, 3 times 2/3, that's 2, plus another 2 is 4. Okay. So this is the last tableau, and let's write carefully the variables here. This is gonna be, remember that's P, Y1, Y2, Y3, S1, S2, and the right hand side. Okay. When you reach the final tableau, so this is the final tableau, the only difference compared to the maximum problem is the way you read the solution. Remember, this is the final tableau for the dual problem. The solution of the minimum problem, so the solution of the minimum problem is still for the cost function taken from the last corner. So the minimum value for the original problem is the maximum value for the dual problem. So the max P, which is given here, is going to be the minimum cost function for the original problem. The variables for which the minimum is attained, so x1, x2, x and y values are read or taken from S1, S2 columns. So this time around, the slack variables will give you the values of the x and y in the original problem. So that means x is equal to 1. That's the value in the first slack variable. Y is equal to 1, the value in the second slack variables. So this is because you're going to have as many slack variables as the original number of variables. So once again, the maximum P you get when you solve the dual problem is going to be the minimum C for the original problem. The values underneath the slack variables will be the values for the original variables where the minimum is attained. So go all the way back when we solved this problem via the graphical method over here where I put this star now. And remember that we established already that the minimum is attained for x equals 1, y equals 1, and c equals 4. So that is the only difference. In short, you take the dual problem, you create a maximum problem in standard form, you solve it. When you're done, the maximum P will be the minimum C, and the values for which this minimum C is attained for the variables, for the original variables, are taken from underneath the S1, S2, so from the columns of the slack variables. So on the next page, I'm gonna go over the main steps, just to write them down on the notes, and then we're gonna do another example, this time a word problem from top to finish. So stay tuned for the second part. All right, so let's review in theory basically what you're supposed to do with a minimization problem in standard form. So kind of like an algorithm. So minimization problem in standard form. So suppose you have a minimum problem in variables x1, x2, x3. Okay, so first make sure it is written in standard form, the way we discussed in the previous page. And then the second step, write the coefficients of the problem in a matrix, starting with constraints and with 0 with the objective function. Last. Transpose this matrix. That means you interchange rows and columns. And then interpret this new matrix as being the so interpret this new matrix as, let's say, as representing a maximum problem in standard form. Also known as the dual problem. Okay. Then write the dual problem solve it with simplex algorithm. And then finally, when you're done, interpret the solution. And what we mean by that, there are two things. The maximum P of the dual is equal to the minimum C of the original. The values of x1, x2, x3 for which minimum C is attained are taken from the last row of the dual under the columns, under the slack variables S1, S2, and so on. So when you do this correctly, the number, so you're going to have the same number of x1, x2, x3 as the number of the slack variables in the dual. So this is basically more kind of more briefly described in the help sheet, but this is essentially the plan of attack, so to speak, from the beginning to an end, the way you actually solve the minimization problem in standard form. So as I said on the last part of this lecture, we're going to go over one more example, a word problem, and that will be the end of this chapter. So stay tuned for the last example of today's lesson. All right, so let's take a moment to write this down. Take 5 minutes, 2 minutes or so, and write this down, and then so pause the video obviously when you do this, and then let's walk through the main points of the problem. So we have a company that owns two mines, A and B, and as we go along with the problem, sometimes it's useful to actually not even read it. Well, you read it once from top to finish, but then you can actually read the beginning and the end immediately, just to have an idea already of how many variables you're going to need in the problem. So let's actually read the question, the final question, how many days should each mine operate to minimize the cost if the cost is to operate is $2,000 each day for each mine. So I know already I'm going to have the number of variables equal to 2, right? So let's say x1 is the number of days mine A operates, and x2 is the number of days mine B operates. And then all the data in the problem here is given in terms of stuff per day. So each day we have a bunch of information, and for each mine, right? Okay, so let's write it as we normally do by row. So mine A produces 1 ton of high grade ore per day, and then 3 tons of medium grade ore, and then 5 tons of low grade ore. Mine B produces 2 tons each. 2 tons each type. So for mine B, we're going to write 2 tons in each category of type of ore. Then we have some constraints. The company needs at least 80 tons of high grade, at least 80 tons of that type, at least 160 tons and at least 200 tons right, of the third type. Then we have some cost of production. Each day it'll cost $2,000 to operate. So we obviously need to minimize that part, the cost. All right, so take a moment to write the constraints and then check with me. So the number of days each mine operates is denoted by x1 and x2. So if mine A produces 1 ton per day, therefore in x1 days it will produce x1 tons. So we're going to have x1 plus 2x2. This needs to be greater than 80. So we need at least 80 tons of that type. Then the second condition, 3x1 plus 2x2, that's the production of the medium grade ore. That should be greater than or equal to 160. And then finally the last constraint, 5x1 plus 2x2, this should be greater than or equal to 200. And we need to minimize the cost, which is $2,000 per day. So that means the number of days for each mine is multiplied by 2,000. So we need to minimize 2,000 x1 plus 2,000 x2. So notice this is already a minimum problem in standard form. All right, so we write the coefficients the way we did it before in a matrix format in preparation to come up with a dual. $2,000, 2,000, and 0. Transpose, right? So remember the meaning of this matrix. This is for the variables and for the right hand side. Now we transpose, first column becomes the first row, 1, 3, 5, 2,000, 2, 2, 2, 2,000, 80, 160, 200, and 0. You interpret this as the information for the dual problem, and the first columns will represent the variables of the dual problem. So notice that the number of variables for the dual is equal to the number of constraints of the minimum problem. Next step, write the dual max problem in standard form. Each row is a constraint for a dual problem, for a maximum problem in standard form. So we're going to have y1 plus 3y2 plus 5y3 less than or equal to 1,000. 2y1 plus 2y2 plus 2y3 less than or equal to 1,000. Maximize p equals 80y1 plus 160y2 plus 200y3. Proceed with the simplex algorithm. Introduce the slack variables. Notice there's going to be only 2 of them, which is exactly equal to the number of slack variables, to the number of variables in the beginning of the problem, x1 and x2. And of course, move everything on the left side on the P row. Come up with the simplex tableau, the initial simplex tableau. We're going to write the basic variables later, right? So in the order P, Y1, Y2, Y3, S1, S2, right hand side. We're going to have 0, 0, 1, 1, 2, minus 80. let's see, 3, 2 minus 160. Y3, 5, 2 minus 200. The slack variables. And let's have fun with the pivoting now. By the way, notice I go a little bit faster, but pause all the time. I mean, many of you should go a little bit faster than in the beginning anyway, because by now you should be familiar with the whole algorithm, but always pause to see if you understand each step, what I'm gonna do, what I'm doing basically. What about the first pivot? Well, that's gonna be actually 2, because the ratios are 2000 over 2, which is 1000, and 2000 over 1, which is 2000. So the least ratio gives you this pivot. And let's divide by the pivot first. So we're going to do row 2 divided by 2. So let's do this in 2 stages. 0, 1, 3, 5, 1, 0, 2000. 0, 1, 1, 1, 0, 1 over 2, 1000. 1 minus 80 minus 160. Oh, I didn't have enough room here. Minus 200. 0, 0, 0, and then remember the pivot is over here. And then on the next stage we do row 1 minus row 2, and obviously 80 row 1, no, excuse me, 80 row 2 plus row 3. Let me see if maybe I shouldn't do that, but I mean, I'm trying to squeeze them side by side, but let's see if that works. So 0 minus 0 is 0, 1 minus 1 is 0, 3 minus 1 is 2, 5 minus 1, 4, 1 minus 0, minus 1 half, right, from 0 minus 1 half, and 2000 minus 1000, that's 1000. 0, 1, 1, 1, 0, 1 half, 1000. Now 80 times row 2. Plus row 1, so that's 0, 1 and 0. 80 minus 160 is minus 80. 80 minus 200 is minus 120. The next one is 0. 80 times 1 half is 40 plus 0, and 80 times 1000 makes it 80,000 plus 0. So notice as you move along with this algorithm, if you practice enough, you don't have to track these labels all the time. You can do that at the end of the algorithm. You can write the labels in that stage. And now let's figure out the next pivot. This is still not the final tableau, obviously, because we still have negative entries on the last row. And the next pivot should be in this column. And let's see, the least ratio is 2, right? Because it's coming from 1000 over 1. 1000 over 2. 1000 over 2 is 500. That's the least row. So that's the next pivot. So let's divide by 2 the first row. So that's going to be 0, 0, 1. 4 over 2 is 2. 1 over 2 minus 1 half over 2 is minus 1 over 4. And then 1000 over 2 is 500. And don't forget, this is the pivot. 0, 1, 1, 1, 0, 1 half, 1000, 1, 0, minus 80, minus 120, 0, 40, 80,000. Okay. Moving on, we're still not done with the pivoting operation, right? Because we need to now multiply row 1 by, we do row 2 minus row 1, and then 80 row 1 plus row 3 to make zeros below the pivot. So we're going to copy I should have left some room here, but we'll do it. Let's see. So we copy the first row, 0, 0, 1, 2, 1 half, minus 1 over 4, 500. Then 0, 1 minus 0, 1 minus 1, 1 minus 2 is minus 1. 0 minus 1/2. 1/2 minus negative 1/4. You can write it on a scratch paper here. That's like 1/2 plus 1/4, which is actually 3/4. 1000 minus 500, that's 500. Now 80 row 1 plus row 3. 100. 80 times 2 is 160 minus 120, that's 40. 80 times 1/2 is 40 plus 0. 80 times minus 1/4, that's minus 20 plus 40. Let's see. Let me double check something here. One zero zero 40. 80 times 1/2 is 40. Why did I write this minus 1/4? Minus 1/4. 80 times. Just 1 second. I want to make sure I don't lose track of this. Minus 1/4. And so 80 times 80 times 1/4. Oh, sorry. Yeah, I got 80 times 1/4 is minus 20. No, that's all good. It's 20. Yeah, I got sidetracked with one thing. So 80 times minus 1/4 is minus 20 plus 40 is 20. Yeah, and then finally 80 times 500, that's 40,000, and you add it to 80,000, that's makes it 120,000. Okay, so let's double check. All good. Yeah. All right. So this is the final tableau because we're done with the negatives on the last row. And let's write now the labels. This is for P. This is for Y1, Y2, Y3. And for the slack variables S1, S2, and the right-hand side. Notice I don't bother at this point with the basic variables because since this is the dual problem, the solution is going to be read underneath the slack variables. So I got that the maximum P, which I know according to the algorithm is the same as the minimum C of the original problem, all the way back to the original problem. So the minimum possible value of C is 120,000. This will be dollars because you minimize the cost, and the minimum is attained for the values of x1 identical to the values under the slack variables. So x1 will be 40, x2 will be read under the next slack variables, which in this case is 20. So the minimum is attained for x1 equals 40, x2 equals 20. And you can check at the end if you want, if you plug in 40 for x1 into the objective function and 20 for x2, obviously you should end up with 120,000. Okay, so that's the reason we don't bother with the basic variables, because the values of x1, x2 for the original problem are underneath the slack variables when you're done with the dual problem. So I hope that's clear. Make sure you go slow on the homework and bring questions. And that'll be it with the simplex algorithm. We will revisit matrices at the end of the class. For now, we're going to focus for a while on a different chapter, namely probabilities, and that'll be the next lesson. And that's it for today.